Good afternoon. I am Jordan Lin. I'm the VP of Capture at Allen Control Systems, or ACS. ACS is a venture-backed defense tech startup out of Austin, Texas. And our mission is to create autonomous precision weapon systems to safeguard our military and allies, ensuring dominance on every battlefield. So right now, our largest near-peer adversary is producing one FPV drone for every second, right? And unfortunately, if the next war were to happen today, the largest hurdle that would ultimately prevent us from achieving victory is that we have just yet to capture battlefield economics, right? And so battlefield economics really to us is it's the fact that we are using very exquisite, very expensive weapon systems to counter highly attritable, low-cost weapons like drones. And so for ACS, we decided, instead of trying to go toe-to-toe with a country much larger than us on the manufacturing side, we decided to lean in and get hyper-obsessed with the cost per kill metric, which is really what gave birth to Bullfrog. So Bullfrog is a full kill chain autonomous weapon station that is designed to detect, identify, track, and defeat groups 1 through 3 drones. The system is designed to be operated 100% passively and to leverage service common weapon systems like the M240 that you see right here. So if I had one with me, and I tried getting it through security, but if I had one with me, you can just literally drop an M240 within 15 seconds, set it up, and you're good to go. So this is SearchCam, and so SearchCam is ultimately what enables Bullfrog to be a passive system. And so what the SearchCam is doing is it is providing, it's passively detecting and recognizing objects using an internal threat library, right? And it's doing this in a fully hemispherical way. And it's doing this with an array of EO/IR sensors, I should say, but I really want to emphasize the fact that this is happening 100% passively. So there's plenty of active sensors like radars that are really good at locating objects in 3D space, right? But there's just significant SIGINT risk when you're using these sensors, especially when you're a unit that's trying to maintain a low profile, not compromise your geo, and this is what really enables any unit to provide a defense in depth without taking on that risk. As you can imagine, computer vision is a big part of Bullfrog's capabilities, right? Not just on the detect side, but also on the identify and the track piece. So right here, Bullfrog is tracking a Group 1 drone, and it's essentially waiting for that operator in the loop to give it that defeat command. And so, one of the challenges with engaging a small, fast-moving object is not necessarily the linear velocity that that object is moving at, but it's really the unpredictable nature that that object displays, right? And the way that I guess when I say unpredictable nature, I'm referring to the acceleration, the deceleration. And so that's where our predictive modeling comes in. Right now, Bullfrog is capable of engaging targets that are accelerating up to 5 Gs. And this ultimately enables us to play shots in a predictive or a proactive manner as opposed to a reactive manner. On the computer vision side right now, within defense, AI ML teams are struggling with data starvation. And for any CV model to be performant, it needs a data set. It needs ample amounts of data. And what we are doing is all of our CV models are leveraging synthetically trained data. And this enables us to do a few things. Well, first, I'll back up. So the process we use is we are taking real-world imagery. Let's say maybe it's from a military parade that Iran does. Iran comes out with their latest Shahed 149. We can pull that real-world imagery. We can put it into our Unreal Engine 5 pipeline. And we can create millions of hyper-real, perfectly labeled images that are tailored to your specific environment, your geographic locale, your cityscapes, landscapes, lighting conditions, everything so that they're relevant to you. And then we can validate that on real-world imagery. And two things happen because of that. One, Bullfrog knows exactly what the operator knows exactly what Bullfrog is looking at. So maybe I don't know who exactly is flying it, but I know it's a Shahed 149 and I know it's coming right at me. Two is that it enables Bullfrog to dictate where its point of aim is. Not always will it be center of mass. Sometimes it'll be a critical component. It'll be a fuselage or a payload. In terms of actual kinetic effects, Bullfrog ultimately enables an M240 to conduct as close to precision fires as possible, right? So without adding any additional MOA. And as a former infantryman, this really warms my heart. Bullfrog is also a closed-loop weapon system. All right, so what does that mean? So Bullfrog does not need any additional human input in order to make that defeat after that target track has been delivered, after the queuing has happened, right? And so the reason why that matters, I think, is because what's the goal of every unmanned system? Unmanned systems ultimately should reduce cognitive burden, not add to it, and that's what we're doing here with Bullfrog. So right now, Bullfrog is contemplating 44 variables in real time. That number is going to continue to scale. I think our founder said next year it could potentially be at 150, 160. But if you distill that complexity down to 3 components, this is really what you would be looking at. It would be mechanical, computer vision, and ballistics. And so, when you talk about precision and optimizing accuracy for a turret system, it really begins with the mechanical system. And the problem with most electric mechanical systems is that you can tell it the same thing twice and you will get a different outcome, right? And so a lot of the legacy remote weapon stations that you see, the ones that are using PID controllers, they are not factoring in certain or most real-world constraints, right? They're not factoring in things like max motor torque, turret inertia. And so what we have with Bullfrog is really, it's a system that is hyper physically aware of what it's doing. The other impact, or I should say the other constraint, is computer vision, specifically on the latency side. And the reason it's hard is not necessarily because we have latency, but just determining what that is, because it's dynamic, it's always changing. And on top of that, also having to figure out what the latency is going to be in the very near future, as in like the next half a second, right? So Bullfrog is sampling the world at a rate of 190 frames per second, and it's ingesting all this and ultimately giving it to our ballistics table. And so when you do it right, this is ultimately what it looks like.
There we go, 114 out. In or out. Oh wow, yeah. It's not gonna hurt you guys.
So I love this slide because it gives a great look as to the evolution of the Bullfrog. The one on the left is our initial prototype, which you saw doing most of the shooting in that video. The one in the middle is our production variant that led to our first sale ultimately. And then the one on the far right is the current model that we're working on now. And believe it or not, Bullfrog is only 8 months old. Our baby robot, Bullfrog, got its first kill last August at Trex 24.2. And so we're scaling very fast, right? But the reality is we have to scale fast. We have to scale fast because autonomous lethality is scaling fast, right? And so I can't tell you the future. I don't know how the use cases are going to evolve, but I will tell you that ACS is dedicated to leveraging robotics for the application of defense. So I look forward to seeing you guys at Happy Hour.